All right, so once you've written this down, then we can start going ahead and writing the equation for it. Now, because we are going up by a given percent each year, that tells us that we're going back to that a of t equation. And so I'm going to start by writing a of t, although I will tell you right now, write it in pencil because I'm going to be making a tweak to that here in a moment. We go a of t equals, next up is p, the principal. What is the principal value in this problem? Yes, it is the 150, because that's what we start with. At the start of the problem, we have 150. That makes that principal. And then I'm going to multiply that by 1.04. Now, if you don't remember where 1.04 comes from, remember that is that 1 plus r. And to get r, I take the 4% and I divide it by 100. So 1 plus 0.04, that's where we're getting the 1.04. And then that's to the power of t, power of time. What is time here, though? We don't know. In fact, yeah, that's what we're trying to figure out, because we're being asked, how long will it take? So I'm just going to call that t here. Now, right now, this gives me a good equation. This equation is valid. The only problem is there's two unknowns. I can't solve it yet. But fortunately, I do have one other piece of information that's going to help here. The 350 needs to go into that equation someplace. Now, I start with 150. I'm looking to see when will I have 350. That is, I'm looking for a final value of 350. So what letter represents the 350 here? The a value. More precisely, the whole a of t. So erase a of t and replace it with 350. Because we're looking to see when would this give us, at what t value will this give us 350. That's the new part today, is writing it like this. Once you've written it like that, you're going to solve it the way that you've been solving your exponential equations. So from here, do as you've been doing. So now that we've written the equation, in order to solve it, I need to get the exponential part by itself. In this case, then, that means getting the 1.04 to the t by itself. And so in order to get that 1.04 to the t, rather, by itself, I got to get rid of the 150. Right now, it's 150 times that amount. And so I'm going to divide both sides by 150 in order to get rid of the 150. Now that I've done that, I have the exponential part by itself. Now, when I do that division, that gives me 2.3 repeating. And so I'm just writing it as 2.3 with a little line over it. After having just done that, of course, that means that on my calculator right now, I'm seeing 2.3 repeating. I'm seeing that 2.3 going on forever. Do not press clear on your calculator, because you're going to want to see that here in a moment. All right, but before we deal with that part, I still need to solve this out. I'm trying to solve for the exponent. What function is used to calculate an unknown exponent?
Log.
Yeah, log. That's why log exists. Log exists for figuring out what an unknown exponent is. So I change it from exponential into logarithmic form using the same rules that I've always used. The base of the exponential becomes the base of the logarithm. Log always equals the exponent, and so on. Having done that, this is now a value that we can calculate. And so in order to calculate it, I'm going to start by rewriting it using the change of base formula. So now I have log of 2.3 repeating over log of 1.04. Now, I haven't done anything else with my calculator since I got that 2.3 repeating, which means that still on my calculator, it's displaying 2.3 repeating. I want to use that whole number when I do this calculation. Now, as a way that you can kind of check yourself and make sure you are doing it right and accurately, if we do it right, we're going to be getting about 21.60. But that's only by using the actual 2.3 repeating. If you rounded that to 2.3 instead, you'd be getting 21.24. That would not be correct. So how do you use an unending decimal on the calculator? Do you have to retype in that whole thing? No. But the way you use it depends on what type of calculator you're using. If you're on a scientific calculator, currently on your calculator screen right now, you see 2.3 repeating. You just press log, and it would give you the value of log of that number. You don't have to type it in again. It's already there. Now, if you're on a graphing calculator, it's a little bit different. On a graphing calculator, you press log, and then you have to enter the number. Typical graphing calculators are the TI-83, TI-84. On those, then, what you'd do is you'd press log, and then go second negative. Because you notice right above the negative key along the bottom, it says ANS. And when you press that, you'll now see on your screen log of ANS. ANS means the last answer that the calculator figured out. So it is plugging in where that ANS is, that whole 2.3 repeating. You don't have to type it in yourself. It does it for you. And then once you figured out the log of 2.3 repeating, divide it by the log of 1.04 to be able to get that 21.60. And so then once we get that answer, in this case we do find it is about 21.6. Therefore, we can conclude if we were trying to say about how many years, it'd be about 22 years for it. Now, switching gears a little bit, we're going to be taking a look at some logarithm rules and some ways that we can manipulate logs. And so, in order to kind of see why the log rules are what they are, I'm going to start with a little bit of review of these. Now, you don't have to write these out. But I do want you to think about each one first, because that's what's going to be triggering these memories. All right, I'm going to do x to the a times x to the b. If I multiply the x's, what do I do with their exponents? We add them, absolutely. And so that ends up being x to the a plus b. Okay, what about dividing, like the second one there? If I divide the x's, what do I do with the exponents? We subtract them, absolutely. Good. Okay, what about that third example? If I have a power to a power, so I have x to the a to the b, what do I do with the a and the b there? We multiply them. And so notice these general rules that we remembered in order to be able to do those. If I multiply the x's, I add the exponents. If I divide the x's, I subtract the exponents. If I raise an exponent to an exponent, I multiply those two exponents. Those same ideas work with logarithms, because logarithms really are just ways of manipulating exponents, so they follow the exponent rules. Therefore, while these are going to be familiar, they still then need to go into your notes, and then we're going to practice using these. All right, and so you're putting these into your notes, but I hope that there is that sense of familiarity as you look at them. Of course, they are very different from anything you've seen before, but they're also very similar to the exponent rules, because you'll notice here the pattern. When I'm multiplying inside the logarithm, that becomes addition. Remember, multiplication became addition in our examples that we just looked at. Division becomes subtraction, and an exponent becomes multiplication. And so what we're going to be doing is we're going to be using these same rules now to practice seeing how we can use these to actually manipulate and even simplify some various log problems that we couldn't otherwise deal with, at least as easily. So, please write down the first one, and then we're going to walk through that together, and then we'll progress together on these. So write down the first, log base 5 of 25x. All right, so the first thing we do is we look back at our notes to figure out which rule this is going to be. Now, what leaps out to me and tells me which rule to use is that inside the parentheses here, the 25x really means 25 times x. So it tells me I'm going to be using this rule. Multiplying two things inside the logarithm is going to mean that I'm going to have two logarithms that get added. Now, one thing, the little note here, it's a little detail. You notice the original here is log base b. When I split it up, they both are also going to have to be log base b. The base stays the same. So already I know that when I rewrite this, I'm going to have a log base 5 of something plus log base 5 of something else. Those two somethings, they're the two things that are being multiplied together. And so we end up getting log base 5 of 25 plus log base 5 of x. Make sure you're writing that down as we go. Now our instructions for this problem is to expand the logarithm. So I just expanded it. I split it into two logarithms. But then it says simplify. Well, simplifying logarithms normally would mean if there's two of them, make them into one. But that wouldn't make sense for it to be saying, take this and rewrite it back where we started from. So when you see something that looks like that where it says expand and simplify, it means expand it, but then look at each of the parts and see if any of those can be simplified individually. And in this case, you notice one of those can. Log base 5 of 25. What does log base 5 of 25 equal? 2. Because remember, log base 5 of 25, that just means 5 to the power of what is 25? And 5 squared is 25. So that's why that's 2. The log base 5 of x, well, that's an x. We don't know what it is, so we cannot simplify that any further. So that's as clean as it gets right there. 2 plus log base 5 of x. We're going to repeat the process with the second one. So write down that second one now. And then after you've written it down, take a moment, think through which rule would you use, what result would that give, and then we'll walk through it together. All right, so for the second one now, the thing that jumps out to me as I look at it is that I'm doing division inside of the logarithm. That tells me that it looks like this rule, because this one has division inside the logarithm. So it tells me that when I expand it, I'm going to split it up into two logarithms, and I'm going to be subtracting those two. And just like before, they both have to have the same base. So I know it's going to be log base 3 of something minus log base 3 of something else. In this case, because we're dividing and then subtracting as well, order does matter here. And the first one, the order didn't matter so much because we were adding. Order with adding doesn't matter, but here we're subtracting. It definitely has to be in this order. You have to be log base 3 of 9 minus log base 3 of x. That's the way that has to be written. And then, now that we've done the expanding, we do check and see, can this be simplified at all? Can I simplify either of those two logarithms? Yes, actually. Log base 3 of 9, that simplifies. Log base 3 of 9 equals 2. Because 3 to the power of 2 is 9. And then that's as simplified as that one will go. So now we go on to the third. Write down the third if you haven't already. And then we start by figuring out which rule we're going to be following. And in this case, what's telling me which rule to follow is the fact that I have an exponent on the inside of my logarithm. And so since we have that exponent on the inside there, that tells me that I'm using the third rule that you wrote down to your notes. And so then with this rule, you notice what happens to that exponent. So then that exponent ends up being taken outside of the logarithm. So since it was to the power of n comes outside. In this case, it's to the power of x, so x comes outside of the logarithm. You notice everything else about it stayed the same. The base stays the same, and whatever was raised to the power of x, it stays in there. So now it's x times log base 4 of 64. Now I look to see, can I simplify that at all? Well, the part that we could simplify potentially would be log base 4 of 64. Does that simplify nicely? Well, 4 to the power of something equals 64. Is that a nice, pretty number? Yes, actually. It's 3. So really, that just equals x times 3, which is correct, but I don't really want to leave it as x times 3, so I'll write my final answer then as 3x. So this big, complicated-looking thing here, it just equals 3x. So these rules allow us to manipulate these logarithms in such a way that it makes them so much easier to work with. Like, what if we were trying to find a value? Well, it's a lot easier to find log base 5 of a number than trying to multiply that number by 25 and then figure out the log of it. Or it's a lot easier to do 3 times a number rather than 64 to the power of that number and then trying to figure out log base 4 of what. Also, another way to look at this to make it easier, what if we were graphing them? We haven't talked about what a 25x would do to our graph, but we do know what adding 2 to the graph would do. So these manipulations allow us to turn these logs into something a little bit more useful. And it can work both directions. In this case, we were seeing what can happen if we expand it out. I also want to take a look at some examples where we go the other direction and actually simplify them into single logarithms. So write down this first example here. We're adding 2 logarithms. And as you're writing that, a little note here. You notice both of these logs are base 3. The fact that they both have the same base is what's going to allow me to do anything to them. If they did not have the same base, I'd be done. There'd be nothing I could do with different bases on them. All right, so first up, I notice that I'm adding 2 different logarithms. So then I need to go back to my notes and I need to see what am I going to be using for my rule. In this case, because I'm going from expanded into simplified form, that means I'm going from the right side to the left side. And so I want to use that rule. I want to use this one that has the logs being added. And so if I add the logarithms, I'm going to turn it into a single logarithm. And notice what happens inside of that logarithm here. I'm going to be multiplying those 2 numbers. So in this case, it was x and y. So it all turns into log base 3 of x and y. And since it's x times y, I'm just writing it as xy. Now, simplify, that can't be simplified any more than that. It's already a single logarithm. There's nothing I can do to manipulate xy, so that one's done. So then we go on to the second one, write down the second problem there. And you're going to find that this one's going to be a little bit more involved. Because in this second problem, there's actually 2 different things going on that we're going to have to deal with. First, you notice that I'm multiplying each log by something. So I'm going to have to figure out how to get that 3 out from the multiplication point. The other thing that's going on here is I'm adding them. So I'm going to have to use the rule that deals with adding logarithms. So then I'm actually going to use both of these. Now in terms of which order to do them in, I suggest just follow the order of operations. I'm going to deal with the multiplication part first, and then I'll deal with the addition part. So, what does the multiplying do? Well, notice I'm multiplying something out front, just like this rule is. And so that becomes an exponent on the inside. So it's going to stay log of 2, but the 2 is now going to be cubed. The same thing happens with the second one. The 3 goes inside the log there as an exponent as well, so that's why it's 5 cubed. Now at this point, I could go ahead and deal with the addition, but I can actually make my life a little bit easier if I do something else first. Because it's 2 cubed and 5 cubed, they're nice pretty numbers. Go ahead and figure out that 2 cubed is 8 and 5 cubed is 125 and write them that way. It's just a little bit cleaner to look at and understand. All right, so now knowing that we have log 8 plus log of 125, I now can deal with the addition. What does the addition tell me to do to the 8 and the 125? Well, notice if I'm adding them, what do I do with the 2 numbers? Multiply them. So it tells me that I'm going to multiply 8 by 125. What is 8 times 125? That does give us 1,000, yeah. So we now have log of 1,000. The question is, can that be simplified? Well, one little side note, let's make sure we remember. What's the base of this logarithm? Because I haven't been writing one in. It's got to be 10, yeah. Because I started with no base written, so it was always a 10. So really it's saying 10 to the power of what is 1,000? Is that a nice pretty whole number? Yeah, it is. It's just 3. So this whole thing here at the start, it just equals 3. So you can see here the rules can also be used to actually figure out a much simpler way to know what that answer is. I could have started this problem by using a calculator to do this, but I would have had to rely on the calculator to do it. But you notice that by doing it this way, I didn't need a calculator for a single step of that. Now, last 2 examples. I'd like you to please write down both of these examples and try to figure out what they both would equal, hopefully without a calculator. You won't actually need a calculator for either of these. But be very cautious. One of them is simple and straightforward. The other one is a curveball based on what we've been doing today. But it's one that we have to deal with. Otherwise, we run the risk of mixing up a couple ideas. All right, so for the first one, we're subtracting 2 logarithms. That tells me that I probably want to be using this formula. Notice I'm subtracting 2 logarithms here, subtracting 2 logarithms here, it matches up. So that tells me I'm going to turn it into division on the inside. So it tells me it's going to be log base 4 of 32 divided by 2. And we can actually figure out a lot of stuff here without even using our calculator. Because 32 divided by 2, that's just 16. And log base 4 of 16, that's 4 to the power of what is 16? It's just 2. Because 4 squared is 16. So that whole thing equaled 2. We didn't even need a calculator for it. The second one. This is where things get interesting, though. Because you see the division there, and you're probably thinking about this rule, because this is the one that has division in it. But notice the difference here. This rule has the division happening inside of a single logarithm. This is a logarithm divided by a logarithm. I can't actually use that rule there. Although you actually have a rule that you can use for solving this. It's actually one that you've been using for a few days now. Isn't this really just the change of base formula?
You can't do that. That's funny.
And so then I'm really starting with this, and I can turn it into this. So it's log base 2 of 32. And is that a nice, pretty number? It sure is. It's just 5.
You tricked us. That's not.
Now we had to deal with that situation because otherwise we do tend to think that this and this are going to give us the same results. And we need to be reminded that it does depend on whether it's log of two things being divided or if it's a log divided by a log and that they get treated separately.